Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we have reached the last module of our course, and here in this module we will discuss the mechanics of friction spinning, and we will start with the process development, how the friction spinning process is developed with time. Now first let us see what is the principle of operation. Okay. So, friction spinning system is based on the principle of open end spinning. So, initially it was based on open end spinning, but later on we can actually insert a continuous filament or continuous drafted fiber strand also in that case, but the principle is actually based on the surface friction. Okay. Now we can see here, this is the schematic diagram of the friction spinning process, where the opening and individualization of fibers from the sliver, okay, either it can come from the single sliver or multiple slivers, and this is done by the opening roller. Okay. And in opening, it is just like we have seen in the rotor spinning. Here also we can use single sliver, but majorly we use the multiple slivers, typically 5 to 6 slivers we can use. Now these opened fibers are reassembled again and form the fiber layer. So, these individualized fibers fall on the surface, that is suction surface, and there it is getting again reassembled. And why do you need the suction surface? Otherwise this surface moves. Okay. This surface suppose moves in a direction, and if there is no suction, the fibers will simply float and it will fly away. So, and we cannot have any other friction mechanism which will actually press the fiber against this perforated surface. So, that is why we need one perforated surface with the suction. We can have a plane surface, suppose one plane surface is moving, and if the fibers fall on it, then what will happen? The fibers simply fly away with the air current or maybe this movement of this surface. That is why this moving surface is made perforated. So, this perforated, through this perforation air suction is there. So, due to this suction force, the fibers are sticking on the this surface, and it is coming under action of another roller. So, metallic roller, which the surface of that roller, surface motion of that roller is opposite to this moving surface, flat surface. So, there at this point, where this at the nip point, close to nip point, the twisting takes place because of the rolling of this fiber assemblies. Whatever fibers are coming, this due to this relative direction of motion, these fibers get rolled, and then these fibers are pulled. This fiber, this is the formation of yarn, then the yarn is pulled in right angle to the axis, to the actually motion, direction of motion. So, withdrawal of the resultant yarn. So, we now then resultant yarn is withdrawn. And this involves the feeding of mixture of fibers and yarn. So, here what happened, after the opening, the fibers are moving along with in the air stream. So, fibers and air are fed, okay, to the moving perforated collecting surface. This is the collecting surface, okay, and this perforated collecting surface, and below this collecting surface there is a suction system. So, as we have explained, we have discussed that collecting surface, we need perforation to actually have the, to make sure that fibers are sticking on this, are placing and moving along with this surface. Now, the fiber assembly is consolidated owing to the twisting by the friction force in the spinning zone. This is the spinning zone, and here there will be friction force. Okay. So, due to the friction force between the metallic roller and the fiber, fiber will start rolling, that twisting will take place. If there is no friction between metallic roller and the fiber, in that case metallic roller will simply slip over the fibers. Then the resultant yarn, okay, this is the resultant yarn, that is withdrawn in the perpendicular direction, okay, of the moving surface. So, this is the moving perforated surface, and the resultant yarn will be withdrawn in this direction, perforated, that is perpendicular to the perforated moving surface. So, here mainly yarn formation is taking place. This is the basic principle of friction spinning. This process is also known as mechanical aerodynamic spinning process, because we need aerodynamic motion of the fibers. The fibers should stick to the surface aerodynamically, and the frictional force, which actually mechanical frictional force is required for twist impulsion. That is why it is called mechanical aerodynamic spinning process, from the fact that spinning effect produced exclusively by the movement of two spinning bodies, okay, in the same sense, okay, they will be moving, and this friction, in this case the friction is mainly by the metallic roller, but in the latest development, the both the surfaces they apply friction. So, here also the friction is applied. Basic fact is that they should, in at the nip point, their direction of motion should be reversed. Otherwise, if the metallic roller moves in the anti-clockwise direction here, what would happen? So, in reverse direction, so that they will simply take the fibers along with it, which is not the principle. Here some friction has to be generated. So, at the nip point their movement should be, the motion, that the direction of motion should be reversed. Now, let us see the history of development. So, this is the principle, and this principle is adopted for every development. And first, Platt Sackolwell, that is master spinner, they actually have patented this technology in 1967. So, this is the schematic diagram of that technology. So, what is there? In this process, the individualized fibers were fed through the feed duct. So, that is the sliver, and from this is the feed duct, from the feed duct onto the perforated disc. So, this is the perforated disc by the suction through the disc. So, there is a suction in the disc, this is a suction duct, and the fibers are deposited on the perforated disc. Okay. And the friction is given by the friction roller, okay, which is a solid roller. There is no perforation. These fibers were carried towards the non-perforated solid roller, okay, which is friction roller by the disc, which forms a narrow gap between itself and other roller. So, this is the suction roller and this one is the solid roller. Okay. So, fibers are deposited on the surface and the fibers are carried to the nip point, and the direction of both the rollers are in the same. So, that they are both the rollers are rotating at the anti-clockwise direction, and so the frictional force generated at the nip point, and from there the fibers are, that yarn is actually pulled at the perpendicular direction. Now, try to see the direction of movement of the disc and that of the roller were opposite. So, here you can see although they are moving at the same angular direction, but their direction of motion at the nip point, the bottom one is moving from left to left and top one is moving from left to right. So, there actually the motion at the nip point is opposite. So, that is the requirement for applying twist. Okay. So, this is required that because instead of the fibers being fed through the gap, they were rolled into the tail end of the yarn. So, if the direction was same direction, suppose normally in roller, so this is moving in the left anti-clockwise direction, bottom one moving is clockwise direction. If they are in the same direction, what would happen? The fibers which were deposited, they will simply be thrown out. So, there will not be any twist application. Okay. So, the twisting is done due to the movement in opposite direction. So, twisted by rolling movement. So, there will be a rolling movement. So, the thing what happens here, this is the top one, bottom, this is a perforated suction roller, and now the fibers are coming in this zone. So, suction roller attracts the fiber due to the suction arrangement, and here this is rotating in anti-clockwise direction, and suppose this is rotating in say clockwise or opposite direction. So, now let us see, this one is rotating in anti-clockwise direction and this is rotating in clockwise direction. Okay. So, though both the things are anti-clockwise direction. Now, here the top one, suction one is taking the fiber, and at this point what happened, there is a friction between the fiber and the solid roller. This is the solid roller, and also due to the suction force here, okay, there will also be friction against the suction roller and the fiber. So, what will happen here, the fiber will try to roll due to the friction. Okay. So, there will be rolling action. So, twisted by the rolling movement and draw off along the gap. So, at this gap there will be rolling movement. Owing to the more advanced stage of rotor spinning, at that time PSL could not pursue this development. So, this development could not be pursued because by that time, okay, 1960s, the rotor has developed. So, people were actually, that was commercially successful. So, this development was actually not taken, it was could not be commercialized. So, after that the drape friction spinner, which is developed in 1973 was developed. Okay. This is the drape 1 friction spinner. In this system the components are, this is the drafting unit, here is the single drafting unit where a number of slivers are drafted, okay, and then the opening roller individualize the fibers, and then the fiber stream is guided through a fiber channel, transport channel, and on the, this is fiber stream on a perforated, single perforated drum. There will be there is a single perforated drum, and the yarn is withdrawn. So, here the twisting takes place due to the friction between the perforated drum. So, here is the perforated drum is there, and the yarn is pulled in the perpendicular direction to that of fiber direction. Okay. So, that is yarn take up, and ultimately we are forming the yarn. This is the principle of drape 1's friction spinning. This is the first spinning, where in the drape 1 friction spinner the opened fibers were made to fall onto the vacuum slot of a single perforated cylinder. So, there is a, it will fall on that single perforated drum, okay, the rotation of which imparts the twist in the fiber assembly. So, due to this rotation there will be twist inserted in the fiber assembly. So, owing to the absence of positive control over the assembly fiber, so this there is no positive control. Okay. So, here there is no second drum. So, that is why there is a much slippage occurred between the fiber assembly and the perforated roller, because no positive friction was given, only the force, normal force is actually we get from the suction, and as there is much slippage was there, the problem. So, twist efficiency was very poor. So, this development, so drape 1 could not be commercialized. So, that was the concept actually was actually proposed, but in future drape actually came up with the modified version. So, which was in 1977 drape 2 friction spinner came in existence. So, that is the first serial drape 2 machine appeared on the market and was the first friction spinner machine, which is actually commercially and practical operation with the. So, earlier machines was there is a theoretical concept, but this was the machine where first practical commercial machine was developed. So, this is the system here, where we have inlet sliver. So, a number of slivers are fed, and then there is some inlet rollers. So, little stretch may be given there, but this inlet roller, from their inlet roller the carding drum, that is opening roller is there, and from the opening roller fiber moves to the that is the fiber transport channel, and due to the centrifugal force fibers come out to the transport channel, and to help this fiber extraction the air is blown, and then the fibers move vertically downward and fall on the drum, that is suction drum. So, there instead of earlier in drape 1 there was a single suction drum, here they have come up with a double suction drum, and these suction drums are also they act as a spinning drum. Okay. And then the yarn formed at the nip point, and the yarn is pulled, the twisting takes place here, and then yarn is drawn out at right angle to this. So, two perforated friction drum with internal suction. So, the suction system or internal suction system, and they rotate in the same direction. So, that they are in this picture they are rotating in the anticlockwise direction. So, that at the nip point there is a rolling action take place which imparts the twist. It essentially consists of a specially designed system. Okay. That inlet system is specially designed which retains the sliver and provides required draft. Okay. Here the inlet system, as I have mentioned, there will be certain draft. These drafted slivers are opened into individual fibers by the rotating drum. Okay. So, this is rotating drum which is called opening roller, and it is covered with the sawtoothed type of clothing, and these individual fibers are stripped from the carding drum by centrifugal force. This is the centrifugal, due to the rotation of the carding drum there is a centrifugal force, they are stripped off, and which is actually supported by air stream. Air stream helps for better stripping, and then they are transported through the transport channel and fall into the nip of the two perforated friction drums. Okay. And they are held there by suction. So, if suction was not there, suppose this is not a solid roller, for on any solid roller there will be a air current generated, and in that case when fiber will try to fall, due to the centrifugal force and air current, fiber will not reach to the nip point, they will be flown out. So, for that there is a negative air pressure is created due to the by the suction. Okay. The fibers are subsequently twisted by mechanical friction on the suction drum. Here mechanical friction will be created, and here both the surfaces are imparting the twist. So, suction through the perforation of the drum assist this process. So, they assist the sticking of the fibers on the surface and also the normal force. Okay. And beside this suction force also help in the cleaning of dust and dirt. So, through the suction slot the dust dirt can be actually removed, and also that will help in production of cleaner yarn. So, this suction drum has got two functions, one is imparting twist and second is that the cleaning of dust and dirt particles. And after drape 2 in 1982, they have come up with their modified version, improved version, which is drape 3 machine. Okay. And to have better yarn quality and also finer yarn. So, finer yarn we can develop, and here in the drape 3 we can produce multi component yarns. So, here we can produce 3 different components. Okay. One maybe one is the core filament we can use, and core staple fiber we can use, and the sheath staple fiber we can use. So, we can use the multi component yarn for specialty application. This is the drape 3 system. We can see here this the slivers which forms the sheath, a number of slivers are there, and typically 4 to 5 slivers we feed, or 5 to 6 sliver we can feed here, and here it is a drafting unit 2, they are drafted by drafting unit 2, and here we can feed the core feeding. The core is normally filament, or we can use the staple yarn also. So, core is fed here through this. So, core is fed, then another drafting unit 1, where a single sliver is drafted. Single sliver is drafted, just normal ring spun yarn, normal ring frame. Okay. Here it is a drafted at high draft, and it goes along with the core, that is continuous yarn or filament, and this 2 forms the core, and they moves, and during this movement through the suction drum, the staple fibers which forms the sheath falls from the drafting unit 2 through the transport channel. So, effectively if we remove the drafting unit 1 and we do not feed core filament, this system will be exactly like drape 2 system, and in drape 3 only thing we have added 2 additional component, one is the core feeding, another a drafted strand feeding, that is staple core also you can feed. So, here we can see that we can produce a multiple permutation combination, yarn different permutation combination, and in the core we can use any filament, any continuous strand. So, there is no limitation, and we can produce a wide range of yarn. Okay. And here the spinning aggregated, actually spinning aggregate where fibers are actually aggregated, and here mainly it is twisted. One thing we should remember here, in the core portion effectively there is no twist. Okay. Either they are slipping over that, or they slips, or there is a false twist, and false twist, during false twist particularly the drafted strand in the core, they are being locked by the sheath. So, there may be some twist present there, but core and draft unit 1 theoretically there will be a false twist. So, unlike drape 2 and master spinner, the drape 3 is not the open end spinning. So, this is not the open end, because here continuous filament or continuous drafted strands are there. Okay. but the coarse sheath type, this is the coarse sheath type friction spinning, it is not the open end friction spinning. So, we should not get confused. So, open end spinning is drape, open end drape 2 is the open end spinning, but drape 3 is a coarse sheath type friction spinning. On this machine, an attempt is made to improve the quality of the yarn by laying some fibers in an aligned fashion. So, here we can have fibers in aligned fashion. So, by laying in some aligned fashion. So, here in the core staple fibers, we can align the fibers in the axial direction, so that the strength we can manipulate. So, this is the portion where the from drafting unit 2 the fibers move to the spinning zone in an aligned fashion. The remaining fibers are wrapped around the core to form sheaths. These are the remaining fibers. So, there are two components from the left feeding zone and another from the top. From drafting unit 2, the fibers are coming and they form they are wrapped around the core fibers to form sheath. So, these sheath fibers are attached to the core fibers by false twist generation here. So, here the false twist generation will be there on the core portion, but the sheath will be simply wrapped around that. So, two drafting units are therefore used to this system. So, drafting unit 1 and 2, one is for core staple fibers, another is for sheath staple fibers. This system produces a variety of coarse sheath structure and multi-component yarns. Okay. So, we can use different type of materials to get the coarse sheath structure, and high performance yarns can be made, and with a delivery speed, very high delivery speed here, because of the presence of the core. Now, after that drape 5 friction spinner came. Okay. The problem of drape 2 system or drape 3 system was that the fibers fall vertically, okay, and then there is a sharp change in direction. So, fibers are falling from the top, say for the sheath in case of drape 3 and drape 2, all the fibers are falling, and then suddenly sharp change in the direction with a right angle, and which actually which results the buckling of fiber. So, that was the problem in drape 2 and drape 3, and also the problem of drape 2 and drape 3 is that the more number of slivers are required, generally 5 slivers for better and even core covering. So, where we need more number of slivers, that is why it only can produce the coarser yarn. Okay. And 5 slivers generally we require for yarn formation in drape 2, and for drape 3 we need proper core covering. So, for that we need large number of slivers. So, and in case of drape 5, the number of slivers are 1 sliver we can use, and also the fibers are not fed at right angle to the movement of the yarn. They are not moving at the right angle. So, buckling, chances of buckling is reduced. So, what is the process? The development here is that this is the suction drum, spinning drum, in other direction, other side also there is a double suction drum is there like drape 2 and 3, but here the fibers are coming in certain angle, not the right angle direction. Okay. As an improvement in this aspect, draft 5 friction spinner was developed jointly by Slaforst, Schuschen and Ferrer. Okay. They have developed this system. Here the individualist fibers from the sliver, okay, single sliver here we can use, this is a single sliver, are fed through the closed or partially opened fiber duct. This is the closed fiber duct, or it may be partially opened at this point near the spinning drum, okay, onto the spinning nib at an acute angle. It is not the 90° or like that. So, it is an acute angle, the angle is very low. Okay. So, they are stretched as far as possible when the fibers are fed into the nib. So, they are not buckled. Okay. One single sliver is fed and fed through the fiber duct. Today's state of the art situation, the drape 5 system is at present the optimum technical solution, okay, for friction spinning to produce a good quality yarn, okay, and with a finer count. So, they can produce up to 15 takes. Okay. So, 40 is any. So, that is a finer yarn and with a production rate of 200 meter per minute. So, this is the system where we can produce a staple yarn with a finer count and with a better yarn quality. And after that, drape 2000 friction spinner was developed, and it has actually it came in 1999 ITMA exhibition. The machine can produce both S twist and Z twisted yarn without any alteration. So, that we can produce, and here we can produce coarser yarn up to say 14 any or 41 takes. Drape 3000 also developed, and where the it is only for specialty yarn, it is not for in general purpose use. So, yarn made from unusual fiber, composite yarn with special core and sheath structure. Okay. So, this is for special property like protective textiles, and here the main advantage is that we can change the speeds infinitely. So, here the drafting unit and opening head, okay, with infinitely variable drive control. So, at any time we can change the draft, we can change the speed. So, twist we can change immediately, which is not possible in easily in the earlier versions, and there was some limitations. The spinning unit with 2 infinitely variable suction spinning drum. So, suction spinning drum speed we can vary, winding unit speed we can vary. So, that everything we can change. So, the drafting unit can handle the different types of fibers. Basically, it is used for specialty fibers such as aramid, FR. Okay. So, this type of specialty fibers we can use, and drape 3, that is it is not a spinning process for mass production. For mass production we can use drape 2 or drape 3, and here this is only for niche market, because here the cost of production will be high. So, for a niche market we can use this product, this machine. Now, coming to the technical descriptions, we will discuss the different zones. First is the fiber feed zone, where fibers coming from the sliver and they are opened. Now, we can see in the friction spinning machine, this unit consists of a single drafting unit. Here is a single drafting unit, inlet rollers, which provides small draft just for, it is not for the reduction of the linear density, it is basically for straightening of fibers and little bit hook removal. Then it comes to the opening roller, pair of opening rollers, and an aerodynamic fiber stripping arrangement. This is the aerodynamic fiber stripping arrangement. Now, this is the total fiber feed zone. Now, single sliver drafting, then the opening rollers and aerodynamic feeding system, fiber stripping system. And due to the suction present at this point, the fibers will be actually coming to from the, it will be stripped from the opening roller, and also due to the centrifugal force. Now, drafting unit consists of two pairs of inlet roller, which retains the sliver, normally 5, and provide the required drafting. The drafted strand of sliver is opened by pair of opening rollers. They are subsequently stripped off by air current and deposited on the nip of the spinning drum. The individualist fibers are transported through the air current, through the by the air current through the transport duct and deposited on the spinning drum. So, unlike the ring spinning, where there is a single method of fiber feed, that is drafting, friction spinning offers diverse solution of fiber feeding. There are two models which we have already discussed, drape 2 and drape 3, which actually fed the fibers vertically on the this nip, and drape 5 feeds the fiber in inclined fashion. And here this is the drape 5 or master spinner system. So, both these systems, they feed the fibers in the inclined direction. This is inclined feeding that we have already mentioned. In all these methods of fiber feeding, what happened? The individualist fibers, fast moving opening rollers, actually this is from the fast moving opening roller, approach relative to the slow moving spinning drum. So, what is that? The spinning drum are moving in this direction, but the whatever the yarn moving direction, that is fibers are moving from the opening roller at very high speed, then the yarn is pulled, yarn is forming, they are pulled at slow speed. So, this slow moving spinning drum, then what happens there? There are progressively their speeds are slows down. So, 1/5 of the approximately 1/5 of the original value, and which results the buckling of the fiber buckled and disoriented, and which causes the weak zones in the yarn. So, when the fibers buckled, okay, and forms the yarn which actually results the weak yarn. This is the crux of whole problem in the friction spinning. So, in the friction spinning, the feeding zone is the problem, and where the fiber buckling takes place, and this is actually little bit taken care of by the drape 5 system. So, drape 5 system, we have the inclined feeding. So, buckling is removed, actually eliminated to some to a large extent. To improve the fiber alignment, there are different systems are developed, okay. Parallelizer or paradisc was developed. So, in the drape system by Ferrer, they have actually tried to align the fiber, like fibers are falling say vertically, and in the spinning drum, this is a spinning drum, fibers gets buckled here, and suddenly they turn in a particular direction. So, this direction. So, there so buckled fibers are coming. So, paradisc was developed by Ferrer. What is that? This is the paradisc. Now, fibers are coming, depositing on the nip, and they are pulled, after twisting they are pulled in this direction as a yarn. This is opened fiber. Opened fibers, they are falling right angle downward, and then at the right angle they are pulling. Now, what happened due in this zone, there is a buckling takes place. So, in this zone the mainly fibers get buckled here, okay. The paradisc, what happened mechanically, they try to align the fiber in the direction of the yarn, okay, yarn delivery direction. How they are doing? This type of paradisc is there, okay. When they rotate, due to this their fibers are coming into action of this projection, and at that time they align the fiber in this direction before it is twisted, okay. This is the paradisc. The disc consists of fan like unit. This is a fan like units are there, located in the fiber flow line, okay, of the opened fiber as they descend onto the yarn forming zone, and the beater blades, this is the beater blades, deflects the fiber vertically, okay, down, okay, and parallelize the towards the yarn axis. So, the fibers are deflected towards the yarn axis, so that the buckling is reduced. So, which results the improved yarn strength. This is a paradisc system, and the use of compressed air also is there. So, here it's you can see we can use the compressed air. So, in Barmack system, this is one is the fiber flow direction, fiber is coming from the opening roller, and the compressed air is fed in the transport channel, and here is the then yarn is moving. So, this compressed air allows the fibers move, and in the and there is a removal of any hooks in a straight fashion, and pneumatic solution is also there here, okay, which is proposed by Platt, okay, Platt Sackel system. In the drafting channel, what they have done, one suction system is created. Okay, this suction system helps in alignment of fibers. Okay. So, oblique fiber feed method. Okay. So, that is in master spinning. So, that is at certain angle we have already discussed, where fibers are fed at a certain angle. Okay. Now, here what happened, incorporation of secondary suction roller duct. So, one is the suction duct, another is the secondary suction duct is incorporated at the end of the transport duct. So, at the end of the transport duct there is a secondary suction duct, okay, is incorporated, which actually helps in orientation of fiber. So, basic problem was actually the fiber orientation. So, these are the different approaches by which the fiber orientation are improved. Okay, secondary suction duct, and Ferrer jointly with the Susen, they have developed the draft 5 system, as we have discussed, where fiber alignment is improved. So, yarn strength was improved. This represents the current optimum solution for fiber feeding and the production of finer yarn. Okay. This is the optimum solution here. Now, coming to the after the fiber feeding, now coming to the yarn forming zone. So, yarn forming zone consists of the friction elements. Okay. Several kinds of friction elements are developed. In general, all these fall into 3 broad categories. 3 broad categories, what are these? Double drum system, single drum system, and drumless system. So, let us discuss this, that is a friction element. So, single drum system includes the disc drum and belt drum. So, here we can see in the draft 1, which is a single drum system. Okay. A disc drum, okay, disc piston drum system was patented by Ferrer. Here the drum operates in 2 quadrant of the disc, rotating speed of the drum can be varied, and delivery speed is approximately 200 meter per minute. Okay. This system we have already discussed, single drum system. Now, drumless system includes, there is no drum, but the belt, 2 disc system or 2 belt system or 2 ring system. 2 disc system, 2 belt system, that is Beltex system, or 2 ring system, ring test system. Okay. Now, see it's which were commonly used earlier in frictions texturing machine. So, false twist texturing machine we used to use. So, here it is a in open end system we get it twisting. So, these are the system. We can see here fibers are entering, and due to friction between this system, now yarn is being withdrawn, and you can see here ring, 2 rings are there. Okay, fibers are being fed here, and it is rolled against 2 rings, and then yarn is being withdrawn. Here you have a belt system. So, there fibers are fed against 2 surface, and then its yarn is coming. Okay. In this case, the fibers must be partly fed outside the friction twisting system. Okay. This process is rather complex, as compared to the 2 drum and 1 drum system. The basic precondition for attaining the spinning actually, that is friction and making reproducible yarn. Here the frictional force acting between the yarn surface and the 2 rotating drums should show as far as possible identical value. So, that friction 2 rotating surfaces, the friction force should be identical. Since the basic conditions was very well defined in the case of double drum system, which are also axially symmetrical system, they thus become the main point of focus. So, the frictional force in the double drum system is mainly important. So, that is actually friction in double drum system, this frictional force actually responsible for applying twist. Now, we can see here in double drum system can have cylindrical, hyperbolic or conical elements. Now, you can see this is the double drum system, this is cylindrical double drum system and these are the conical system. This one A is the cylindrical system and B and C are the conical double drum system. Conical version provides high stability of yarn formation and offers 2 models, okay, 2 modes of yarn draw off. One mode is that draw off over smaller diameter. So, when you are taking the yarn and the yarn is drawn from the smaller diameter portion, okay, and another this is draw off from the larger diameter portion. So, larger diameter portion. So, this is the system, but here the stability is there, high stability of yarn formation is there. Okay. And the design and adjustment of spinning drums, okay, have considerable influence on yarn formation and ultimately yarn properties. What are the design conditions? The shape of the drum. So, the shape of the drums, whether they are more cylindrical or conical, the length and diameter of the drums, okay, because length and diameter they are actually they influence the twist efficiency and energy required. So, if the length of the drum is more, so there is a chance of higher twist applied. The use of 1 or 2 suction drums, the percentage of perforation on the roller surface. So, how much roller surface are perforated, so that the suctional force or frictional force is dependent on this factor. The finish of the friction producing drum surface, what is the friction? So, that will also result frictional coefficient, and the finish and adjustment of suction cover plates. Okay. So, these are the parameters, and process variables are the suction, the amount of suction or magnitude of the suction force, the dimensions and geometry of nips between the drums, the rotation of drum surface, okay, that is what is the speed of the drum surface, and whether they are actually the rotation ratio of the drum speed. So, there may be what is the speed ratio. So, that will actually result in friction, the ratio of rotating speed of 2 drums, the direction of rotation when only one suction drum is used. So, these are the different process variables. the fiber feeding device, the direction of yarn takeoff. So, these are the different process variables for friction spinning. Okay. So, the rotation of drums create desirable friction. Okay. The airflow into the drum causes the force of reaction generating between yarn and the drum. The spinning drum rotates in opposite direction. Okay. And drag force acting on the yarn creates torque which twists the assembly. The resulting twist potential, however, does not correspond to the ratio of the drum diameter to the yarn, since 60% of the loss due to the slippage is there. Okay. For the manufacture of the reproducible friction spun yarn, a constant twist potential is essential. So, if you want to produce the same yarn, so that the slippage, we should control the slippage, and to achieve this it is necessary that frictional force acting on two surfaces do not change. If the frictional force of the surface changes, then twist potential will change, twisting amount of twist will change. So, we cannot reproduce the yarn. Now, we can see here this diagram here, this is the yarn formation here. Okay. These are two friction drum, and due to the suction force the friction is generated. Okay. This is suction force here for drum N1 which rotates and with the speed of NT1, and here it is a NT2, the fibers are coming here, and now the frictional force. So, normal force acted by the drum 1, this is drum 1, here is drum 2 is N1. So, frictional force is mu R1 is mu N1. Similarly, for frictional force by the drum 2 will be mu N2, where suction force is N2. So, this suction force are different. So, the friction force are calculated according to Coulomb's friction law, okay, and multiplying by the friction coefficient of friction is multiplied by the normal force generated by the suction. In order to obtain the same normal force on two contact areas. So, normal N1, make it N1 equal to N2. Okay. The spinning nib must be evacuated from both sides. Okay. We have to create the almost same frictional force. Three options exist for evacuation of the nib of the two friction drums. One is evacuation of both spinning drum in the nib, evacuation of one spinning drum in the nib zone, evacuated drum being the one rotating out of the spinning nib, and evacuating one spinning drum in the nib, and the evacuated drum being the one which is rotating into the spinning nib. One is the out of the spinning nib, another is into the spinning nib. So, this is the spinning nib. So, what is one is moving out, another is moving in. So, option A and B were covered by Ferrer patents until 1990. Okay. That was the, and third option C refers to the Platt system. So, these are the different options to get the friction. The evacuation of single drum results in energy saving and economic process. However, when one drum is evacuated, especially if this is not one rotating out of the nib, it cannot be avoided that some of the fibers which cannot be integrated are transported out of the nip zone. So, that they may go as a fly. Because of this option, the plate friction spinning, especially the spinning of cotton, fly, lint and dust, they comes out from the nip point. On the other hand, the evacuation of both drums avoid the kinds of this problem. So, if we try to have suction in the both drums, this type of problem does not exist. So, diameter of the yarn of medium count is 0.2 and the fiber duct used in the friction spinning in the feeding of the individual fiber must have opening width at least 3 millimeter to generate trouble free transport. So, that should be at least 3 millimeter. In evacuating the friction zone from both sides, okay, the resultant of the two air flows, okay, there is a two air flows that this two airflow component is exactly vertical to the nip. Okay. So, that will be that resultant will be exactly vertical to the nip. So, that the fibers guided okay, into the spinning nip and are immediately integrated into the yarn. So, that should be vertically exactly at the nip point, and moreover the friction coefficient between two friction draft must show almost equal value. So, mu for both the drums must be equal. If this is not so, then there will be slippage between the friction drum. So, that should not, then that will reduce the twist efficiency. Okay. And we will stop here, and we have discussed the friction spinning basics. They are at different zones, the fiber feed zone, the transport zone and the friction zone, and where the yarn is formed. Okay, till then, thank you.